Did you know? Before electricity was a way of life, ancient Egyptians were aware that lightning and shocks from electric fish were very powerful. They used to refer to these fish as the thunderers of the Nile. Today, we'll explore the intricate world of electric current in our modern society. But before we venture into the realm of electrons and circuits, let's begin with the fundamental question. What precisely is electric current? Electric current is the rate of flow of electrons in a conductor. In other words, it's the movement of tiny particles called electrons through a material that can conduct electricity. The SI unit of electric current is the ampere. Our ancestors relied on fire for light and cooking, but today, we have instant power with the flip of a switch. Devices like toasters, ovens, TV, and mobile phones all need electric current to function. Electrons, tiny negatively charged particles, carry electric current when they move. The ability of a material to conduct electricity depends on the number of free-moving electrons it has. So, remember, not all materials conduct electricity equally well, and it's the movement of electrons that powers our modern world. It's like a magical flow of invisible energy that keeps everything running. Let's quickly solve a question to revise what we have learned. Electric current originates from which part of an atom? The correct answer is negatively charged electrons. Based on their ability to conduct electricity, materials are classified into three categories: conductors, insulators, and semiconductors. Let's kick things off by unraveling the mysteries of conductors. In certain materials, the outer electrons of each atom or molecule are like adventurous spirits, only weakly bound to their parent atoms. These electrons are often referred to as free electrons or conduction electrons. When we introduce an electric field to such materials, these free electrons come to life, moving in a direction opposite to the field. It's almost like an electrifying dance party happening inside the material. Such materials are what we call conductors. Now, what materials can conduct electricity? Well, the list includes some surprises. You'd expect metals like iron, silver, and gold to be on the list, but did you know that even the human body can conduct electricity? It's true. So, the next time you touch something and get a slight shock, you're experiencing the magic of conduction. But here's a spark of intrigue. Among all the elements, silver takes the crown as the best conductor of electricity. Now, let's move on to the second category: insulators. In the world of insulators, all the electrons are firmly bound to their parent atoms or molecules. There are no free electrons to create the dance we see in conductors. When we place an insulator in an electric field, the electrons might shift slightly in the opposite direction, but they can't leave their parent atoms or molecules. It's like a dance where the dancers don't really move, they just sway a bit. These materials are also known as dielectrics. Now, let's talk about the fascinating realm of semiconductors. At low temperatures, semiconductors behave much like insulators. All their electrons are snugly bound to their atoms, and there's no room for movement. But here's where it gets interesting. As we crank up the temperature, a small number of electrons begin to break free from their atomic shackles and join the conduction party, responding to the applied electric field. But here's the plot twist. The behavior of semiconductors doesn't rely solely on temperature. Other factors, like doping, come into play. Doping involves introducing impurities to modify the electrical properties of the material. It's like adding secret ingredients to a recipe to change the taste. Because semiconductors have far fewer free electrons compared to conductors, their behavior falls somewhere between that of a conductor and an insulator. Hence, the clever name, semiconductor. In semiconductors, when a freed electron moves, it leaves behind a vacant spot in its normal bound position. These vacancies, known as holes, also play a role in conduction, adding an extra layer of complexity to the dance of electricity in semiconductors. Let us solve a quick question to revise what we have learned. Which of the following is the most conductive element? The correct answer is option C. Silver. Silver is one of the most electrically conductive element. This is because electrons can move more freely in silver than any other elements. Silver also has the lowest contact resistance of any metal. Let us now explore the fundamental unit of electric current. Magnitude of electric current is measured in coulombs per second. The SI unit of electric current is ampere, denoted by the letter A. Ampere is defined as 1 coulomb of charge moving past a point in 1 second. To put it simply, if there are 6.241 into 10 raised to the power 18 electrons flowing through our frame in 1 second, the electrical current flowing through it is 1 ampere. That's a mind-boggling number of electrons racing by. Now, let's discuss some practical applications. The unit ampere is widely used within electrical and electronic technology. You might have heard of terms like milliampere and microampere. These are handy multipliers, especially when we work with smaller electronic components. Properties of electric current. Electric current is not just an abstract concept, it's the lifeblood of our technological world. Can you imagine life without electricity? It's almost impossible. So, let's explore what electric current is and some of its properties. We know that electric current is the result of the flow of electrons. This flow of electrons does something remarkable. It's responsible for generating electrical energy. Electrical energy can be converted into various forms, like heat energy or light energy. For example, in an iron box, electric energy is converted into heat energy. Similarly, when you turn on a light bulb, the electric energy is transformed into light energy. It's incredible how one form of energy can transform into another. Now, there are two main types of electric current: alternating current, AC, and direct current, DC. Direct current flows in only one direction, while alternating current changes direction periodically. Direct current is often used in low-voltage applications, like charging batteries or in certain aircraft applications. On the other hand, alternating current is what powers our homes, industries, and commercial establishments. As mentioned earlier, the electric current is measured in amperes. It's worth noting that 1 ampere of current represents 1 coulomb of electric charge moving past a specific point in 1 second. This means that 1 ampere equals 1 coulomb per second. Now, did you know that the direction of current flow might not be what you think? The conventional direction of an electric current is the direction in which a positive charge would move. So, the current in the external circuit flows away from the positive terminal and towards the negative terminal of a battery. It's a little counterintuitive, but understanding this conventional direction helps in simplifying our circuit analysis. What is Ohm's law? Moving on to Ohm's law, which is a fundamental principle in the world of electricity. Ohm's law states that the voltage across a conductor is directly proportional to the current flowing through it, provided all physical conditions and temperature remain constant. This law is named after the scientist Georg Simon Ohm, who made significant contributions to our understanding of electrical circuits in the 19th century. The basic components of current electricity are voltage, current, and resistance. Ohm's law gives us a simple formula. Voltage, V, equals current, I, multiplied by resistance, R, often written as V is equal to I times R. It's like a mathematical recipe for understanding how these three quantities are related. But what's the C unit of resistance? It's called the ohm and is denoted by the symbol omega. To illustrate the concept further, when we have a given resistance, the ratio VI remains constant. In other words, if we graph the potential difference, V, against the current, I, it forms a straight line. This linear relationship is a powerful tool for analyzing electric circuits. Ohm's law makes solving problems related to voltage, current, and resistance in electric circuits much simpler. It's a foundational concept in electrical engineering and essential for understanding how electricity behaves in various devices and systems. Let us quickly solve a question to revise what we have learned. In which of the following cases is Ohm's law not applicable? The correct answer is option C, insulators. According to Ohm's law, it is applicable only to conductors. Hence, Ohm's law is not applicable in case of insulators. Ohm's law magic triangle. Let's discover a magical tool to simplify calculations for voltage, current, and resistance. How the magic triangle works. Imagine a triangle with V, voltage, at the top, and I, current, and R, resistance, on the other two sides. This triangle makes solving Ohm's law equations a breeze. Now, let's put it to use. Calculating voltage, V. When you need to find voltage, V, just cover up the V at the top of the triangle. This leaves you with I and R, or, more precisely, I times R, so, the equation for voltage becomes V is equal to I times R. It's like a magic trick, where you multiply the current by the resistance to get the voltage. Let's apply the magic triangle to a real-world situation. Say we have an electric iron with a resistance of 50 ohms and a current of 3.2 are flowing through it. To find the voltage between 2 points, we use the formula we just learned. V is equal to I into R. Now, let's substitute the values into the equation. V is equal to 3.2 amperes times 50 ohms is equal to 160 volts. Isn't it fantastic how the magic triangle simplifies the calculation? You just multiply the current, 3.2 amperes, by the resistance, 50 ohms, and there you have it. Applications of Ohm's law. Ohm's law isn't just a theoretical concept. It's a practical tool used in various applications to determine the voltage, resistance, or current in an electric circuit. It's essential in maintaining the desired voltage drop across electronic components, ensuring that they operate optimally. Ohm's law finds application in DC ammeters and other DC shunts to divert current for measurement. Limitations of Ohm's law. While Ohm's law is incredibly useful, it does have its limitations. Ohm's law doesn't apply to unilateral electrical elements like diodes and transistors, as they allow current to flow in one direction only. These devices have unique electrical characteristics that Ohm's law can't describe. For nonlinear electrical elements with parameters such as capacitance or resistance that vary with time, voltage and current won't remain constant. Ohm's law becomes less useful in these cases. Understanding Ohm's law, its applications, and its limitations will equip you with valuable knowledge as you delve deeper into the world of electronics and electrical circuits. In this video, we've delved into various essential topics, including the concept of electric current, its unit of measurement, the properties associated with it, and exploration of Ohm's law along with its practical applications and limitations. We'll further explore the remaining topics in the upcoming video.